Welcome, everyone. Thanks back for lunch. This is the first session in Freya. If you have any questions for the speaker, please just post them in Ask Freya on the Slack channel, and we can address them afterwards or at a later stage. Without further ado, it's Akilesh, and he's going to be talking about real-time content delivery.
Hi, everyone. So lunch was really awesome. So it's really good sandwiches. So is anybody actually awake? Or it's like I saw so many people yawning and being like relaxing chairs. Just right. So, are you watching closely? Anybody seen The Prestige? You like it? Awesome movie. So if you haven't, please see it. It's a wonderful movie. And if you don't remember anything else from this talk, please see this movie. So I feel good. It's an honor to be here. My name is Akilesh Gupta. I am a real-time engineer at LinkedIn. And today I'll talk about real-time content delivery. So it's a mechanism to push real-time content from your backends to your apps and make them come alive with dynamic experiences. So what is real-time content delivery? One of the most obvious ones is something as simple as typing indicators. If you have a chat application, delivering an instant notification that the person that you're talking to is typing is really useful. How many of you know about Periscope? Cool, it's popular here too. So watching a live video while seeing real-time likes and comments stream in is the quintessential Periscope experience. It's a lot of fun. Even on desktop, Facebook has been experimenting with real-time likes and comments and typing indicators as someone interacts with your post. The entire Uber app experience has its appeal based on real-time content delivery. The position of nearby cars, the location of the driver, the real-time sharing of your ride, they're all live dynamic experiences. So how do they do this? Let's try to answer some of those questions today. So the first thing that comes to most people's minds when they peek behind these experiences is a concept called polling. So one way to simulate real-time updates in the app is to ask the server every few seconds whether there's something new that is available for consumption. A simple HTTP GET request is made to the server, and it happens at a well-defined frequency f. So whenever the server has some data to send back, it provides a response on the next GET request. So as an example, the app could potentially poll for new likes and comments that are happening in the Periscope app every X seconds and update it on its UI. But there are some major problems with this approach. A lot of times, the poll request is wasted because there's nothing new on the server to send back. Like you don't always have a new thing to send back. Secondly, the frequency f of the polling is a double-edged sword. If you make it too high, it results in unnecessary traffic. And if you make it too low, there's delay in information dissemination, right? So those are the problems. Still watching closely? Okay, so you've got to solve this for me. Let's take another example of semi-real-time technology. So I had planned a movie with some friends and was getting late for the show. So at 3:16, I told my friend that I'll be at the multiplex. The movie was playing in 2 auditoriums, and I didn't know which auditorium I was supposed to be at because that's where my friends were. So my friend messaged me, and he said that he was in auditorium 6. I still ended up in auditorium 7. Why? What's the problem with this picture? No? Anyone?
Didn't receive the message?
Sorry?
Didn't receive the message?
Well, I received the message, I just received it too late. So my friend sent the message at 3:17 a.m., whereas I received it at 3:19, right? Because LinkedIn messaging at that time was push notification based, and you just have no control over when a push notification will arrive when you're using push notifications. So that was what we had before. Because a push notification travels via either APNS or GCM, you simply don't have enough control over it. It can be slow, it can be unreliable, and it can be throttled for various reasons. Moreover, you're bound to certain size constraints, depending on the kind of OS that the client is running. Moreover, certain real-time use cases just cannot be implemented with push notifications. It would be really hard to do something as dynamic as the Uber app experience with just push notifications. So this gets us to the real-time technology platform that we built at LinkedIn. My goal is to give you the building blocks that we used at LinkedIn so that you can easily replicate it on your own stack, whatever stack you may be working with. So you don't have to rely on any third-party vendors, and you don't have to rely on any complex new protocols. So let's take a look at some basic requirements for a real-time delivery system. We need a pipe over which data can be sent between the server and the client. We need a way to identify the kind of data that a server can provide. We need a way for the client to inform the server what data it is looking for. And we need a way to actually deliver the data in real time to the right client. So if you have seen publish subscribe systems before, this maps pretty cleanly to a connection and defining topics to identify groups of data that a client may be interested in, and letting clients subscribe to those topics to identify what are the topics that the client is interested in. And then you finally publish data on the relevant topics. So let's see this a little more visually. We need a persistent connection between the client and the server, and the client can be termed as a subscriber because it subscribes to topics that it is interested in. We need a system to actually manage and store information about these subscribers. So let's call that the pub subsystem that is backed by a database to store the subscriber information. So as soon as a new client connects, we need to store the new subscriber information in our database. So that's step number one. Next up, the client needs to be able to specify a subscription because it needs to tell the server what it is interested in. So subscription to a topic, it basically defines the kind of data that it is interested in receiving. As an example, it might want to subscribe to typing indicators that I showed you earlier, or it might want to subscribe to Periscope likes and comments. The pub subsystem also needs to store the subscription somewhere, and that's why we have the subscription database. Finally, when an event happens on the back end, so let's say there's an event happening, somebody sending a typing indicator, a new like happened, a publisher needs to be able to publish the event on the topic. So let's say this is the event that happened, it needs to be able to publish it. This system needs to be able to deliver that typing indicator which was published to the client using the subscriber and the subscription information that it has. So this is the basic setup, and it needs 4 building blocks: the connection, the subscriber, the subscription, and the publish. So I'll spend the presentation talking about how we did each of these things at LinkedIn and how you can do it in your apps. Nearly everything that we did can be replicated in any stack that you may be working with. So let's start with the connection. The first thing that happens is that the client connects to the front-end server over a persistent connection, a persistent pipe. In our case, the front-end server is a Play Java front-end, but it can be anything that you have. Let's talk more about the nature of this connection. So we chose to use a technology called HTTP Longpole, which is a regular HTTP connection where the server simply holds on to the connection and does not disconnect after sending back a response. Over this Longpole connection, we use a technology called server-sent events, which allows us to stream chunks of data to the client without the client needing to make subsequent requests. And event source is the interface that is used to actually send these chunks of data to the client. So the client request looks like this. The client makes a normal HTTP GET request, and it sends an accept header, which is text/event stream, which defines the format in which it will accept the event source data. The server responds with a normal HTTP 200 OK, but the content type is set to text/event stream, and the connection is just not disconnected. Chunks of data are sent down without closing the connection. As you can see in this example, each chunk is simply a line of text. It starts with data, and it has some information which can be JSON, it can be any other payload that you might have. We chose this protocol as it provides the maximum compatibility with the LinkedIn user base. because it's just regular HTTP, nothing special going on here. And with most cases, you will find that this is actually good enough for your use case as well. So without closing the connection, the server may later send an object over the same pipe. So you first received a typing indicator object. On the same connection, you later receive a message object. And then you can have a location object. Each chunk is processed independently on the client through this interface, which is called the event source interface. So as you can see, there's nothing terribly different about this from a regular HTTP request, except this content type header and the fact that there are multiple response chunks that are happening over the same body. So how does this look like on the client side on web? So the client first creates an event source object with the target URL, and then it defines event handlers. So for each chunk that streams down from the connection, you actually get this event handler to fire, and you're able to parse the data and convert it into a reasonable object that you need. So if you actually go to this URL, you can actually see this in action. If you're logged into linkedin.com, I can actually show you. Oops, sorry. Oh, it's not letting me click it, but if you actually click on that URL and you try it on your browser, you will actually see that the connection is just held, and you will see that streams of data is being sent on that connection. So if you need to support IE, there are many polyfills which emulate the event source interface. IE is the only browser which does not support this natively, and you can use polyfills for that. Similarly, there are lightweight open source libraries that you can use for different clients for the event source interface. On the server side, almost every major server framework supports the event source interface natively. You don't need to install anything different. At LinkedIn, we use the Play framework, and we use a regular Play controller to accept the incoming connection. We then use the Play event source API, which is this one, to make it a persistent connection. So the moment we use this API, it becomes a persistent connection. And we assign it a random connection ID, just to identify that connection. Now we need something to manage the life cycle of this connection, right? Because it's going to live for a certain amount of time. This is where we use this concept of an ACA actor. An ACA actor is used to manage these persistent connections. So for those who don't know, ACA is a toolkit for writing highly concurrent distributed applications. It uses this model called the ACA actor model. We create one actor per incoming connection to manage these connections. So every time a new connection comes in, we create one ACA actor. Since this is a mobile conference, I won't go too deep into the ACA part of this, but there is immense documentation on how this can be used to manage persistent connections. So the natural question that I get asked when discussing our technology is WebSockets. Server-sent events or event streams support unidirectional communication, like you can send data from the server to the client. WebSockets, on the other hand, support bidirectional communication. You can send data both from the client to the server and server to the client. But there are some caveats, and it's very, very important to understand them. So the few things that you should keep in mind are as follows. It's generally not a good idea to rely on WebSockets as the first and only connection mechanism. The reason for that is that there are many proxies and firewalls and antivirus systems that actually block WebSockets. So if you are serving users across the world, you might run into users who simply cannot use WebSockets to connect to you. And it's also not available as an upgrade over HTTP2. So if this happens to be your connection mechanism, which a lot of clients are moving to these days, then you cannot upgrade to WebSockets from an HTTP2 connection. So it's actually much better to establish an event source connection first and upgrade to WebSockets when possible, so that people who are able to support WebSockets are able to use WebSockets, and you also have a fallback mechanism to use event source in general. And there are frameworks like socket.io that can be used to actually do this kind of jumps between these two protocols. So let's also look at the key differences between using vanilla event source and using a persistent connection framework like socket.io. So the event source interface supports server to client push only, as I mentioned briefly, and it works over plain HTTP, so it provides the maximum compatibility. And it has built-in support in most client and server frameworks. You don't need to do anything special. So it's fast and easy, and it's normally really good for most use cases. On the other hand, socket.io supports bidirectional communication. So if you need bidirectional communication in your app, that's when you would go from something easy and fast to something that is a bit more complicated, but it gives you something more. And it supports both the long polling and the WebSockets protocol as part of socket.io. It also has built-in delivery acts if for some reason you need that in your app. And there are special socket.io libraries that you have to use for both client and server frameworks. So it does not come built in. So it's normally used for advanced use cases, and that's when you would use socket.io. All right, so that was a high-level overview of how one can create a persistent connection. And now let's talk about what we need to actually store the information about this connection, because most talks end at the connection part. I want to talk about like how you can actually make this entire system work. So each connection is effectively a subscriber. Once the connection is established, the front-end server assigns it a random connection ID, as I showed you a moment ago. Also, the front-end server has its own front-end server address. This is the front-end server that this connection is connected to. And it's important because there might be multiple such devices which are connected to the same front-end server, and there are multiple such front-end servers. So you need to know which connection ID you're talking about, which identifies the device, and you need to know which front-end server you're talking about so that you know which front-end server this device is connected to. We need to store this information in our subscriber store so that we have persistent information about this connection. So this information is sent to the pub subsystem, and it adds a row in this database for this particular connection. At LinkedIn, this front-end server is a Play Java frontend, and the pub sub server is a Java backend. And the subscriber store is a distributed key value store. But again, the reason why I'm highlighting all of this is that this can be any system that you're used to. It does not have to be Play, it does not have to be Java. As an example, you could use Couchbase for the distributed KV store. So that's how subscriber information is persisted for each client that connects to our system. Now let's talk about the step where the client actually subscribes to a topic, where it says that, hey, I want to receive something. I want to receive a real-time event, which is of kind X. So as an example, a user B, which has been assigned a connection ID, which is this, the connection ID, it might want to subscribe to its own typing indicators topic. So what that means is that B is saying, I want to subscribe to this topic so that every typing indicator that needs to come to me comes to me, right? So that's the topic for B. So going back to our system, the connection ID of the client and the topic that it wants to subscribe to are sent by the client to the front-end server, which forwards it to the pub sub server in this step. And the pub sub server now stores this mapping in the subscription database, which is the second database that it has. Once again, at LinkedIn, this is a distributed key value store, but it could be anything that you want to use. So that's it. So clients subscribe to multiple such topics depending on what they're interested in. Likes, comments, typing indicators, car locations, it can be anything. Now let's look at the most interesting part, which uses all of this information to actually deliver events as they happen to the clients. Everybody with me? Kind of? Right. Ooh, complicated diagram. So clients B and C are connected to our front-end server systems. So these are persistent connections, right? This front-end server is able to talk to our pub subsystem, which has the same old subscribers database and subscriptions database. Now, the interesting part here is that A wants to send a typing indicator to B, right? So it starts with this typing indicator that it has, which it wants to deliver to B. So the first step is that the typing indicator is sent to the messaging backend, because that's the one that actually processes this and owns this typing indicator and can figure out where it needs to get delivered to. So the publisher now has two pieces of information. It has the typing indicator that A typed, and it has the typing indicator topic for user B, because this typing indicator is supposed to go to B, which is the one that B was subscribed to. So it sends these two things to the real-time pub subsystem for delivery. So now the topic that B subscribed to and the typing indicator that A started are both at the pub sub server. Watching closely? Everybody? Cool. So let's sum it up a little bit again. So B connected and was assigned this connection ID. It's connected to this front-end server, right? So that means that the connection ID and the front-end server address for B are in the subscribers table. B also subscribed to its typing indicator topic. And that's why we store this mapping where we say connection ID, which belongs to B, is subscribed to the typing indicators topic for B. So those are the two mappings that we have. Now we have all of this, right? So how do we actually deliver the typing indicator to B? So now it's very simple. The first thing that the PubSub server needs to do is to find if there are any subscriptions for this topic. So it looks up the subscription table, finds that there is a corresponding subscription, and boom, it knows the connection ID which subscribed to this topic. It retrieves the connection ID for user B and looks it up in the subscribers table, because now it needs to know which is the front-end server that B is connected to, because it needs to know where to send this typing indicator. Should it send it to this one or should it send it to this one? So it looks it up from here, and it knows that the connection ID that is subscribed to this topic is this front-end server address, which happens to be this one. This gives it the front-end server address that it needs to send the event to. So notice how it chooses this front-end server and not this one. That's the important key point here. So in this diagram, the PubSub server sends the typing indicator event to the first front-end server, which has the connection with B. Now we have another problem. There might be multiple such connections with this front-end server. So this front-end server needs to know which is the connection that B is connected to. But it has that information because it has this connection ID. So the front-end server uses the connection ID to find the connection to which B is connected, right? Simple PubSub. So because the front-end server has many such persistent connections, it needs to figure out which is the one that B is connected to. And now that it knows, it sends the typing indicator to B, and B gets the typing indicator. So for event source on the server side, it looks something as simple as this. It does event source.send and the typing indicator object. What does this look like on the client? The client has this open connection, and a new chunk of data appears, which says user A is typing, right? And it just displays that on the screen. Finally, all that work for just one typing indicator, right? But the cool part is that the same system works for anything, any real-time experience. We are using this at LinkedIn for multiple real-time experiences, and similarly, this could be used for likes, comments, car locations, anything that you're interested in. So one final thing about these building blocks is that I want to talk to you about some alternatives for the PubSub system that I just mentioned. So there are a few open source PubSub systems that you can use instead of the PubSub technology that I described to you. So I won't go into too much detail, but they are ActiveMQ. That's one very popular PubSub system. There's RabbitMQ, which also does the exact same thing. And then there's Redis, right? So if you're familiar with these technologies, you can replace the PubSub system that I described to you with these open source technologies. So with that, let's talk about performance and scale. To convince you that this system was not built for just one typing indicator, I want to show you some numbers. So we did this experiment where we kept adding more and more connections to the same front-end machine. Like kept going. So we wanted to see like how many potential connections can a single front-end server machine hold. Any guesses? Sorry? A single? Oh my God, please tell me how to do that. Yeah, sorry?
Depends on the memory.
Yeah, it depends on a lot of things. But the cool part is that we were able to manage 100,000 connections on a single front-end server machine. And as he said, there are multiple steps to actually get to this place. So there are some very interesting pieces of engineering that we did to get to that number. And we learned a lot in that process, including memory, Java heap collection, all of that stuff. And we shared all of that on this blog post. So if you're interested in that aspect of the system, please go to this URL, and that will have all the information about how we got to that 100K number on a single machine. The next number I want to share with you is how deliciously fast the system is. Let's take the typing indicator example. If we record the time t1 at which the messaging backend publishes the typing indicator to the PubSub system, And then we record the time t2 at which the typing indicator actually makes it to the destination client. The delta turns out to be just 75 milliseconds at p90. So it's just super efficient. There are no complex queries. There's no computation happening. A lot of the computation has been pre-computed, right, because of the subscribers and the subscriptions. So this whole publish pipeline is really efficient, and that's what you want in a real-time system. So why does the system scale, whether you have a few thousand members at a startup, or whether you have 1 million members or 500 million members as you have at LinkedIn? The reason is that there is no in-memory state anywhere on the system. All entities can talk to any other entity. The state is stored only in this distributed key-value storage systems. And you can simply add more front-end server boxes or more PubSub servers if you need as you scale the system. So it's completely horizontally scalable. All right, so I think I spoke a lot, and this was a lot to consume in the last few moments. So let's take a few things that you should remember as you walk out of this talk. So real-time content delivery enables dynamic instant experiences on your apps. It's just really cool. The semi-real-time technology like polling and push notifications are good for simple use cases. And there are 4 building blocks for a true real-time platform. Those are connection, subscriber, subscription, and publish. Event source or server-sent events are usually great for most use cases. They're fast and easy to implement, and they are built into most server frameworks and most clients, especially web. And then there are readily available client libraries for iOS and Android. So the PubSub platform that I did describe to you, it can be built on any server or storage technology that you're already used to. And it is stateless and completely horizontally scalable. And finally, you should go see The Prestige, please. It's a really, really good movie. So we recently launched online and offline presence indicators on LinkedIn messaging using the same system. So all these green dots that you see are built on the exact same system. It resulted in massive increase in engagement. So perhaps most importantly, you can do the same for your app. It's actually very easy to do if you follow some of these basic steps. And if you spend the time to build the building blocks right, you can actually create many different real-time experiences on your app. So thank you, everyone. I'm a proud Indian. I work at LinkedIn in the US. And I'm so happy that I saw these northern lights in Tromsø. It was beautiful, totally magical experience. Thank you so much, Norway. And you can tweet to me at this Twitter handle, or you can send me a LinkedIn connection request. I would love to answer your questions.